some aspects of harmonic oscillator and its some some simple problems or some discussion around harmonic oscillator, so that we'll get a complete understanding of that. That is what I propose to do. Okay. So I will not repeat the calculation that I have done, but I will try to. Uh, so the harmonic oscillator is the Hamiltonian for the harmonic oscillator is given by p square by 2m. This is of course one dimensional, plus half m omega square x square. Now this is one problem, but this is quite generic in the sense. Um, so I can say that this is uh, very general in the following sense. Okay, so the first thing is that harmonic oscillator is not one problem, but it is a problem that is there in every problem. So this is not a new argument, which you might have you might have studied this argument in your classical mechanics course. Suppose we have let us say that we have any potential. So let's say that let v of x is any potential, is any arbitrary potential. Okay. So in that, and if some x is equal to x star is an equilibrium point, equilibrium, of course I have to qualify this equilibrium further by saying it must be some stable equilibrium point, and if the system is displaced infinitesimally from x star by, let's say, some quantity called eta, then we could write this v of x star plus eta. Eta is very small. It's a small displacement. So I could write this potential in the following fashion: v of x star plus eta into dv by dx evaluated at x equal to x star plus eta square by factorial 2 into d square v by dx square evaluated at x equal to x star, and so on. We will have all the infinitely many derivatives. This is basically Taylor expansion. Now, since so this is equal to 0, since x equal to x star is an equilibrium. And this is, of course, some constant. This is some constant and can be chosen as reference. any constant potential can always be absorbed into the reference. So if I choose this as my reference, that means this can be made zero, and this is already zero. So I have x star is fixed. Now if I have this v of eta, so v of eta can now be written as half. This is basically an approximation, half, and you can write down some force constant value k, and then eta square. Just 1 minute. Okay, sorry. So k into eta square, and these higher order terms we can neglect because eta is much less than 1. That is, since eta is small, uh, these terms of the higher order, higher powers in eta can be neglected. So, so this term is what I'm writing here as half k eta square. So now you can say that the force constant is related to the second derivative of the potential at the equilibrium point. X equal to x. Okay, so the harmonic oscillator potential is quite general, or if you know a particle, or if you know a system with mass m, this k will be written as m omega square. So this is also equal to m omega square. So the frequency is related to the second derivative of the potential. So we are not solving just one problem, but this problem is relevant in any potential for which there is an equilibrium point. Okay, so this is a very general problem. Harmonic oscillator is very general, so it can be used in, in every problem in that sense. Okay, so this is, since I have done one dimension, I am just mentioning about one dimension. But even if you have many degrees of freedom, such notions are applicable. I am sure you have seen this in a chapter in classical mechanics called small oscillations. Okay, so this is my first point, that it is very general problem which is applicable in every potential. Okay, so for all dynamics, so around the equilibrium point, so the dynamics of a system around an equilibrium point, the specific around a stable equilibrium point, is governed by harmonic oscillator potential. And this fact is independent of what is the actual potential. Whatever is the actual potential V of x, this around the equilibrium point, if your displacement is around the equilibrium point, in terms of that displacement, dynamics is governed by harmonic oscillator potential. In that sense, this problem is very generic. Okay, so this is one point that I wanted to make. Now, the second point is what kind of a physical system do we have in mind? Okay, so physical system. Okay, so suppose if somebody is asking you, okay, I have a harmonic oscillator Hamiltonian, and you are doing quantum mechanics of this, but what kind of physical system does this correspond to? Now, classically, we have some picture like this. Classically, we have a picture like this. That is, you have a spring and then a mass, and let's say this is there on some frictionless table, and this is your equilibrium length of the spring, and then you give a displacement to this mass by some amount, so you call this as x displacement. Then, of course, if you consider this displacement as your generalized coordinate, you can write this as half kx square. Now, any system where this kind of oscillator is involved, all these calculations are relevant. For example, there is this Lorentz model, um, Lorentz model for so let's say you have a nucleus, and then there is a spring, and then let's say there is an electron. Okay, so this nucleus and spin and electron, nucleus and the electron and the spring. Okay, so atom is something like this, and now let's imagine that you are subjecting this to an electromagnetic field. Okay, I'm drawing, let's say, only electric field. Okay, an electric field like this. Okay. So then what happens is, because the electric field, this is E field, that means E field is like this in this case, and it is like this in this case. So because the electric field is changing direction at some frequency, this electron will sometimes will be stretched, sometimes will be compressed. So you will have oscillations, and these oscillations are called dipole oscillations. And this kind of oscillations is what Max Planck had considered in describing the black body radiation. So this is another system. So we have uh, so whatever classical system that we are familiar, a similar model is applicable even to atoms and electron in atoms, and then the model for radiation in terms of Lorentz model. So these are some physical systems that we have. I mean, oscillator is, even though I told you that it is not necessarily the system is like that, whatever is your system, but around the equilibrium, it is always like this, a spring block kind of a model. And hence, it is, it is, yeah. So it should be viewed in this fashion. Wherever you have this kind of a model, then you can think of writing this dynamics of the harmonic oscillator are relevant. Now, we'll come back to this physical system a little later, but then let's try to see what is that we have observed. So we have the potential uh, not very symmetric, but okay. So this is a V of x process x. So you can see there are two things. V of x is uh, goes to infinity, as x goes to plus or minus infinity. So this is the first aspect, and this implies that whatever is your psi of x must go to 0 as x goes to plus minus infinity. So this is what is called boundary condition. Now the second thing about this is v of minus x is equal to v of x. What is the consequence of this? So psi of x is either even or odd. That means it is some even or odd. It should have definite parity. Okay, so this is the consequence of the nature of this potential. And we have seen already that in terms of dimensionless variables, that is in terms of xi, which is equal to x by L, where L is equal to square root of h bar by m omega, and epsilon, which is equal to E by E naught, where E naught is equal to h cross omega by 2. So we have the following results. So we have epsilon is equal to 2n plus 1, n is equal to 0, comma 1, etc., which is equivalent to saying that you have En is equal to n plus half into h cross omega. These are energy eigenvalues. And psi n of x is given by 1 by square root of 2 to the power n factorial n into root pi into e to the power minus xi square by 2 into the Hermite polynomial Hn of xi. So this we have seen. So these are Hermite polynomials. Okay. So some understanding of Hermite polynomials is so I would recommend, if you have to get some familiarity in solving problems, I would recommend that get some familiarity with Hermite polynomials. So get familiar with Hermite polynomials. Okay. Um, yeah. So what you have to learn is you have to learn about the orthogonality relation, generating function. We have already used the Rodriguez formula, generating function. Then, of course, using this Rodriguez formula to generate and, of course, some recurrence. If you know generating function, getting recurrence relations is not very difficult. So So this much if you know, then I think you will be able to solve problems where this Hermite polynomials are required. So I would strongly recommend you go back to your special functions chapter in Mathematical Physics 1 that you already studied last semester, and then refresh some of these things for the Hermite polynomials. Okay, so now the point is that we have these wave functions, and now we'll try to um, so if you look at the ground state wave function, that means psi 0 of xi is equal to 1 by root pi to the power half into e to the minus psi square by 2. Now, if you look at this wave function is a Gaussian wave function. So we have xi here, and then it has a Gaussian wave function. Okay, so this goes to zero only at there goes to plus infinity or minus infinity, and there is no node. Node means wave function will become zero there, so there is no node. Okay, and so this is the wave function, and the probability of this one is square of this. That is probability density for the n equal to 0 is basically modulus psi 0 of psi the whole square, which is given by 1 by root pi into e to the minus psi square, which also looks somewhat like this one. Okay, so now note that suppose you want to ask what is the expectation value of xi, which is xi is x, as you know, except for that a constant length factor L. So expectation value of xi, if you ask, that is equal to 1 by root pi into integral minus infinity to infinity psi psi 0 of psi the mod square d psi. But note that so you can ask so we can ask the following question: for any psi n of xi, the expectation value of psi is equal to integral minus infinity to infinity psi psi. You know the answer. We discussed this with respect to a dagger in the last class. So you know this. But now notice that our uh, previous about the potential, you know that psi of x is either even or odd. Now, whatever is psi of x, whether it is even or odd, psi square is always even. Okay, so this is always even. Okay, that is even function, always. Now, psi into psi, this whole thing is always odd function because I'm multiplying with. So, any odd function from minus infinity to plus infinity d psi is always equal to 0. Okay, since integral minus infinity to infinity f of psi d psi is equal to 0 if f of minus psi is equal to minus f of psi. Okay, I am sure you know this. If you do not know, just think a little bit and then you can write down the. Okay, so that is a general argument to say that expectation value of xi in any of the energy eigenstate is equal to 0. Okay. Now, what about expectation value of p? Expectation value of p will also be equal to 0. I do not want to uh, give you the argument, so please generate the argument. Expectation value of p is also equal to 0 for all psi and alpha. So expectation value of psi is equal to 0 and expectation value of p is equal to 0. Now, suppose if you are interested in asking a question, what is the expectation value of chi square, etc., then it will become complicated. Because that time you cannot have an argument, but you have to actually calculate. And calculations are not very easy with respect to these integrals. Okay. So that is where we have to make use of the other method that we have, namely defining these operators A and A dash. Okay, so let's look at those things. So I think I have defined A as square root of m omega by 2h bar into operator x plus I p operator by square root of twice m h bar omega. Or I could have written this as pull out this m omega by 2h bar into x plus ip divided by m omega. Okay, and a dagger is simply the adjoint of this one. So a dagger is equal to square root of m omega by 2h bar into x minus ip divided by m. Okay. Now, suppose you add these two things, that is a plus a dagger. A plus a dagger is equal to square root of 2m omega by h bar into x. This 2 is coming into the numerator because there are two terms when you add them. So this implies your x operator can be written as square root of h bar by 2m omega into a plus a dagger. So this is how you can write down your x in terms of a plus a dagger. On the other hand, if you want to write p, then you subtract. That is, you write a minus a dagger. That is equal to. So that is you have square root of 2m omega by 2h bar into p by m omega. Okay, so this m omega, there is no 2 here, so you have root m omega here. So this implies your p operator is equal to square root of h bar m h bar omega by 2 into, of course, there is an I also sitting here, I, and a minus a dagger. So I can write down x and p in terms of a and a dagger in this fashion. Okay. So You can see that this gets simplified in terms of your, if you want to write this in terms of xi, because h bar by m omega is L, and then x by L if you write. Okay, so note the simplification. Note that xi cap, if you want to write, that is simply 1 by root 2 into a plus a dash. And similarly, this p is written as h bar by I into d by dx. Okay, and suppose I bring this m h bar. So let me retain 2 there and bring that I this side. Okay, so let's write 1 by I into 1 by I, and then I have 1 by square root of m h bar omega, and this h bar will cancel with this. So you have this is equal to minus 1 by I square is minus 1, and then I have square root of h bar by m omega into d by dx. Okay, so now I want to write d by dx as d by d psi into d psi by dx. So that is basically L into d by d psi. Okay, so h bar by m omega is okay. So maybe let me put it this way. So I can write this P is equal to I by so m omega by h bar. So I have to get that. That means I must multiply this with the h bar, right? So m omega by h bar into a minus a dagger. So this is equal to I h bar. This is I h bar by L. I h bar by L into a minus a dagger. That is equal to um, it implies I get L into P. L into P is equal to, there is a 2. That 2, I think I will leave it as such. So that 2 will be there. So that is root 2. So that is, so L by IH bar into P is equal to 1 by root 2 into A minus A dash. Okay. So now what I have is L by IH bar into P. I can write it as H bar by I into d by dx. Okay, so L into d by dx is what I write it as d by d psi. Okay, h bar will cancel. It becomes minus L into d by dx. Okay. So actually what I'm trying to do is that I don't, okay, I think it's not required that I should write P in terms of xi. But let me see, yesterday we did something with this. Yeah, so we wrote this. A dagger in terms of psi minus d by d psi, right? So like this, if you write A, that will be written as psi plus d by d psi. Okay, so then you can write down d by d psi in terms of A minus A dagger. Okay, so that is not T, but you can write down d by d psi in terms of. Okay, but anyway, this is not needed. Okay, I just want you to just play with this, but this is not needed because what we require is only these operators x and t. If I
Hello, I
write
think
any
sir,
terms, these two expressions
hello.
are yes, yeah. Tell me, yes. What is the question? Hello, can you hear me?
So I think he was having some network issues.
Okay, but I am audible, right?
Yes,
Yes,
sir.
sir.
Okay. So one of the important thing which I yesterday asked you to do, and I think some of you might have tried, is to calculate average value of x square. This is important because average value of x square minus average value of the x square is your delta x square. But then we know this is already equal to 0 because we have argued that earlier. Now, to find out average value of x square, now in a state given by energy eigenstate n. So in a state, if you want to find average value of x square, so you have to ask what is n x square operator and n. So then you have, if you write down n, and then you know your x is given by this factor h bar by 2 m omega into a plus a dagger. So you write down this as a plus a dagger the whole square and h bar by 2m omega. The square root will not be there because I am squaring this. So this is given by h bar by 2m omega into, you have n and then you have a square plus a dagger the square plus a dagger. I cannot write 2 a dagger because a and a dagger don't commute. So I write a dagger a. Okay. So which is equal to h bar by 2m omega. So you can write down n a square n plus n a dagger square n plus n a dagger n plus n a dagger a n. Now notice that this a square n will be proportional to, this is proportional to n minus 2 because a will reduce this n to n minus 1 and n minus 1 to n minus 2. And n with n minus 2 will be 0. And hence this term is equal to 0. Similarly, this a dagger square to the n is proportional to n plus 2. And n with n plus 2 is also equal to 0. So this term is equal to 0. The first two terms do not contribute. Now these terms, so now you consider n a dagger n. So this is a dagger n. So now this is basically what happens if a dagger is acting on n, that is root n plus 1, n plus 1. Okay, so that is equal to n a acting on n plus 1 into a factor root n plus 1. But what is a acting on this one? A acting on this one is root n plus 1 n. So that is equal to, now I get n plus 1 into n n. Now this is equal to 1. So this part is equal to 1. And therefore, this term gives you n plus 1. What about this term? So if you consider n, a dagger, a, n. You consider this term, a on n is root n into n minus 1. So that is equal to n, a dagger, n minus 1 into root n. But what is a dagger n minus 1? Is root n, n. So that is equal to n, 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 and this n, n is equal to 1. So we get this factor as n. So what is the final thing? That is your x square is equal to h bar by 2m omega into n plus 1 plus n. So that is equal to 2n plus 1 into h bar by 2m omega. So this is what will be the expectation value of x square. Now you can ask what is the expectation value of p square. Expectation value of p square is, so if you go back to this one, p square is given by this one. So minus m omega h bar, m omega h bar by 2. So minus m omega h bar by 2 into n, a minus a dagger, the square n. So you can see that minus m omega h bar by 2 into n, a square plus a dagger square minus a dagger minus a dagger a. Okay, so there's 4 terms and n. Now you can see that this same argument, like in the previous case, this will become 0, this will become 0. Okay, please don't think that this we have to write separately, and the expectation value of this becomes 0, expectation value of this becomes 0, and this one becomes n plus 1, and this one becomes n. So minus sign will come out, and then you have 2n plus 1 into m omega h bar. Right. So what we have here is x square. But remember, this is same as delta x square. So delta x square, delta x the square into delta p the square is actually equal to x square into p square. In this case, it is not in general true, but in this case, it is like that. So that is equal to, so x square is 2n plus 1 into h bar by 2m omega. 2n plus 1 into h bar by 2m omega. And delta p square is 2n plus 1 into m omega bar by 2. So m omega will cancel. So h square and 4. So that is equal to 2n plus 1 the square by 4. So if you ask what is delta x into delta p, that is square root of this, that is equal to 2n plus 1 into h cross by 2. Or you can pull out 2 from here and write this as n plus half into h cross. So this is an uncertainty in position momentum for a general energy eigenstate. Okay, so this is uncertainty in x and p x and b for a state n, for a state n. Now, uncertainty relation tells you that delta x delta p has to be greater than or equal to h cross by 2. So this is the lowest value that delta x delta p can have. Okay. Now, for n is equal to 0, that is for ground state, delta x delta p is equal to h cross by 2. That means this is whatever is the minimum uncertainty is exhibited by the ground state of the harmonic oscillator. Okay, so now even if you want to talk about higher powers of x and p, or properties like operators like xp or px, anything you can actually obtain by using this relation between x and a diamond. Okay, so this is in some sense the use of our use of this relation between x and p, and calculations become simpler in this case. Now let us look at yeah. So now let us look at some of these wave functions. The ground state wave function, which I have already represented. Okay, so it's a ground state wave function like this. Okay, let's say this will be a psi 0 of x. This is x. And first excited state wave function will be something like this. Okay, so there is one node, that means that x equal to 0, it is 0. And then this is your wave function. So this will be a psi 1 of x. Versus x. Now the probability, if you want to draw the probability will be something like this. This will also be, so this is whatever I plotted here is psi 1 of x. So the negative part also will go up, as you know. Probability is always positive, so mod psi square. So this is how it looks like. Now let's look at psi 2 of x. So psi 2 of x will be something like this. So it will be having two nodes. Okay, so it will be going to infinity only at 0. So there will be two nodes, one node here and one node here. Psi 2 of x and x. Okay, so yeah, so you can see that this is an even function and this is an odd function and this is an even function. So alternately, so psi n of x or psi n of minus x is equal to psi n of x if n is even, 0, 2, like that. And psi n of minus x is equal to minus psi n of x if n is odd. Okay. Now you can see that for odd n, psi n of 0 has to be equal to 0. Because psi n of 0 is equal to minus psi n of 0. Correct? If I put x equal to 0, Suppose if I put x equal to 0, I get x psi 0 equal to minus psi 0. That implies what? 2 times psi 0 is equal to 0. Okay, 2 is not equal to 0. We know that. That implies psi 0 has to be equal to 0. Psi 0 has to be equal to 0. That means odd wave functions are any odd for odd n, psi n of x has to pass through the origin. Now this is somewhat interesting because sometimes you may use this information to answer questions like this. For example, let's say someone comes up and says, okay, let me consider a potential which is equal to like half m omega square x square if x is greater than 0, and then infinity if x is less than or equal to 0. Suppose if this is the potential, then you ask what are the energies and energy eigenvalues of this. Now this potential is something like this. So we have uh, potential like this, and in this region this is infinity. Okay, this is infinity. From this side onwards it is infinity. That means it is like one side it is like harmonic oscillator, and the other side it is infinity. Okay. Now you know that if it is so now you think of region 1 and region 2. Okay. Now in region 1, your psi 1 of x has to be equal to 0. Correct? So this is something because the potential is infinity, the particle will not come to that region at all. There is no probability that the particle is there in that region. So psi 1 is 0. Now psi 2 of x, if you want to solve Schrodinger equation, you have to exactly do the same thing that we have done earlier. So now what happens is that the wave function has to be continuous. Okay, wave function cannot be discontinuous. So therefore, if there is some wave function for the harmonic oscillator which will go to 0 at x equal to 0, those wave functions can be continuous with this one, right? So what we have to do is uh, only those states are allowed, those states among psi n of x of harmonic oscillator are allowed, uh, which go to 0 at x equal to 0. Okay, then only. Okay, so those wave functions exhibit continuity to psi 1 of x, which is equal to 0. Okay, so what is the ground state of this? So the ground state of this potential, that is one side harmonic oscillator, is psi 1 of x. So what is psi 1 of x? Psi 1 of x is equal to same as psi 1 of x of the harmonic oscillator. Okay, so um, let's call this as psi tilde of x. Psi 1 tilde of x is psi 1 of x for x greater than 0, and 0 for x less than or equal to 0. Okay, so that means what we have seen this psi 1 here, right? So in this case, the ground state is going to be something like this. So this is your potential. So this is going to be 0 up to this, and then it will be. Earlier, you remember this was like this. Now this part will become 0. So whatever solid line that I have drawn is actually the um ground state wave function of the new potential. So similarly, this is your ground state. Okay, so what I plotted is I1 tilde F. Now next one, psi 2, for example, at x equal to 0, psi 1 is not 0, so this cannot be state, and x2, psi 2 also will not be 0, so that is also not possible. And we can see that the next one, that is first excited state. So what is the ground state energy? Ground state energy is so the ground state energy is E1, that is equal to 3 by 2 h cross omega. So this is the ground state energy of this oscillator. And first excited state, corresponds to psi 3. Okay. And ground state, first excited state energy is E3. Okay, so that is 3 plus half, 7 by 2 h cross. Okay. So like that, only odd. So for this psi n of x, for n is equal to 1, 3, 5, etc. in region 2, and uh, psi n of x is equal to 0 in region 1. Okay, so region 2, region 1. So this is how you can get, without, you don't have to solve the problem again, but then you can get answers for this kind of questions by looking at the boundary conditions. So what is the change between that problem and this problem? It's only the boundary conditions. So recall that uh, for uh, uh, for v of x is equal to half m omega square x square, the boundary condition is that psi of x goes to 0 as x goes to plus minus infinity. Okay, so now if you think of vector space of functions which satisfy this boundary condition, that will be the solution set for this. Now if you look at this potential for v of x is equal to half m omega square x square if x is greater than 0 and infinity if x is less than or equal to 0, and the boundary condition for this is psi of x goes to 0 as x goes to plus infinity, and psi of x has to go to 0 as x goes to 0. So you have to pick up only a subset of solutions which satisfy this in addition to satisfying this. So all these odd functions will satisfy this condition. Okay, so that those odd solutions will be solutions, I mean the wave functions for the region 2 in which harmonic oscillator is there. Now, the interesting question here is that just like we talked about the physical situation, so can we think of uh, a physical system corresponding to this system? The system is very interesting. In fact, Later we will see we can develop a method called WKB approximation. So we can actually solve and get these energy eigenvalues. Now we are only reading out by inspection, but you can actually solve and get these energy eigenvalues using a technique called the WKB approximation. So we will do that later. But so what is the physical system corresponding to this system? This system means I am mentioning this system, that is half m omega square x square and infinity, this kind of a system. Now there is also another interesting question that one can ask. Of course, I'm asking these questions. It does not mean that I have answers, but when asking questions, we don't have to worry about answers. Maybe we will get answers, maybe we will not get, but questions are more important than the answers. So let's say that I have a potential like this, and I have half m omega square x square on this side, and let's say I have another potential that is half m omega um, omega prime square x square this side. That means the I have two different parabola. This side it is one, and this side it is another. So now we can ask several interesting questions. How will the quantum mechanics change in this case, or how to obtain energy eigenvalues and energy eigenfunctions? Is there a simple way? Okay. Or first you can think of what happens to the period in classical oscillations, and then from there you can see, okay, an effective frequency can be defined and everything can be quantized in terms of that effective frequency. Okay, so now the question is, we have in harmonic oscillator case, you know that since energy En is equal to n plus half into h cross omega, uh, so energy levels are equally spaced. Energy levels are equally spaced. Okay, so does this happen for this also? Okay, these are some interesting questions uh, one can think of. And then, what is the physical? Is there any physical physical system corresponding to this? So, is there a physical system? Suppose you want to do an experiment to see how oscillator behaves in this kind of things. What kind of a physical system should we consider uh, suitable to this potential? So this is another question. Suppose we want to do some experiment in the lab. What kind of system should we choose? So, so these are some uh, issues related to the harmonic oscillator, and of course there are many others, but we can see what more. So there is one more thing that I wanted to mention since we talked about low range model, etc. So let's say that we have uh, harmonic oscillator, the mass in harmonic oscillator potential, or the particle. I don't know, maybe this is 7. So the particle in harmonic oscillator potential, let's say, is charged with the charge q. Now you apply electric field, apply uniform electric field. Okay. So if you apply uniform electric field, then what happens? There is an interaction of this charged particle with the electric field, and that gives rise to an additional term in the Hamiltonian. So Hamiltonian will be p square by 2m plus half m omega square x square, and then there is um, a term which is suppose if I apply q in the suppose you apply electric field in the positive direction. So let's say your electric field is E0 into I cap in the positive x direction. Then you have plus QE into, this is the force that is acting into x. Okay, QE0 into x. Okay, so you have this additional, so this is the potential corresponding to this charged particle. There is also a restoring force. So this is the potential corresponding to restoring force of the spring, and this is the term corresponding to the electric field. Now, what happens if so? If you do quantum mechanics of this system, then what happens? So now we can see that. So I can write down this Hamiltonian in the following fashion. I have to ultimately solve h psi equal to E psi. So I will write this as half m omega square into x square plus, I have pulled out, so I can write down 2qe 2q e naught divided by m omega square into x. Okay, and now I can complete the squares. Okay, that means I want to write this particular thing as some x plus alpha the whole square minus alpha square. So that is basically, that means what? That means my 2x alpha is equal to 2q e naught by m omega square into x. So 2x cancels. So alpha is equal to q e naught by m omega. So this can be written as t square by 2m plus half m omega square. This is one question which is always asked in the interviews. So will the frequency change to try to write this? So x plus qe qe naught by m omega square the whole square minus qe naught by m omega square the whole square. So this is what it is. Now supposing if you write down your h psi is equal to E psi equation. Okay, so you have this term that is, and now let's say that you try to rewrite this. So let's say you redefine, instead of x, you define some die. This die is not same die that I was talking. So maybe you type x tilde is equal to x minus qe 0 by m omega square. This is just a constant shifting, right? And so your d by dx will not get influenced, and hence you can write down this uh, Hamiltonian in terms of p square by 2m plus half m omega square into x tilde the square. Okay, this is the operator part of it, right? This is an operator part. Psi is equal to E plus QE0 by m omega square to the square, this into psi. So I have a different energy level. Okay, so I will call this as some E tilde. So this will be equal to some E tilde psi. Now this problem is exactly same as our harmonic oscillator. Okay, so our E tilde of n is equal to n plus half into h cross omega. Frequency did not change. Frequency is same. Correct. Now But what is E? This implies your energy En. En now can be written as, because E tilde is this, right? So En is equal to n plus half h cross omega, okay, minus this QE0 by m omega square. So energies are getting changed. That is, each energy level will be decreasing by by this effect. So this is the change in the energy eigenvalues. Okay. Yes.
Excuse me, sir. So here x tilde should be x plus q of qe not by
X.
m omega,
Ah,
sir,
yes,
right?
yes. X plus. Yeah, yeah, right. Okay. So now, so what is happening here is that this energy is changing. So if you look at, so V as a function of x tilde is simply half m omega square x tilde the square, right? So, but if you write this in terms of half m omega square into x plus qe naught by m omega square the square. Now you can see that this potential energy has the following form. So when is the potential energy? Um, so at x equal to 0, the potential energy has some value. So when is it exactly 0? So it is 0 at some point which x is equal to minus qe by m omega square. Let's say some point here, and it is of course a harmonic potential. So you can see that this potential will have a shape like this. Okay. So earlier you had a potential which was like this. Okay. So now this potential is basically the form is same, but it is displaced from here. Okay. So this system is generally called as a displaced harmonic oscillator. Displaced harmonic oscillator. But the frequency will remain the same. It is exactly like in classical situation, you have a spring and a block, and let's say this has got certain equilibrium point, and then it is making oscillations around this equilibrium point with the frequency omega. Now, suppose if you hang it in gravity, there is an additional gravitational force that is acting on this, some mg. Then what happens is that the frequency will not change, the equilibrium position will change. That means it is, instead of oscillating around this point A, now it will oscillate at some other distance A prime. That gets the equilibrium position gets displaced. In the same way, this equilibrium position gets displaced. So that is why this is called displaced harmonic oscillator. Okay, and of course this has some interesting consequences, and we will not go into that. So I think it is the time for me to sign off because I have another meeting. So if you have one or two quick questions, I can take, but otherwise,
Hello,
I
sir.
think yes.
Sir, why the uncertainty is also equispaced?
So that is a consequence of the nature of this potential. Okay, it is not in general true, but see the when we talk about uncertainty, um, we can say what is the difference in uncertainty, but spacing between uncertainty is something which we don't have much of a physical meaning. It's an accident that it is also following the same form.
So, sir, can we conclude it's due to the symmetry of the potential?
No, it's not. It's not due to the symmetry of the potential, because symmetry is a very general idea. I can construct many symmetric potentials, but not all of them will have this equispacing. Equispacing is a very special property of the harmonic oscillator.
Okay, sir.
Sir, in the Lorentz model, electric field is changing, so it will create a changing magnetic field. So is it the reason why we got radiation?
Yeah, so the radiation comes because of kind of an acceleration in oscillatory motion. Okay, so that is quite an involved question, but radiation is the oscillating dipole emits radiation because the charged particle will undergo acceleration.
Okay, sir.
Okay, so maybe then I will just uh, stop here and we can continue in the next class. I'm sorry I have to stop it early today.